in the last lecture we had started off with neural networks, and we had seen that how by using very simple processing units called neurons, we attempt to learn different kinds of functions. So, the model that we looked at in the last lecture was what is called a perceptron, and a perceptron is a single layer network where we have neurons which are simple processing units, and we had a set of input units feeding into the neuron. So, we had each neuron was like this, and we had actually a collection of other neurons also, and each of these other neurons would also receive inputs from the same set of input lines, right. So, this was the simple form of a single layer network that we had looked at in the last class, right. And then we wanted to see that how to compute the weight learning function. So, initially all the weights are randomized, and we want to learn the weight learning function, so that after we have learned the weights and we are presented with the inputs, the neuron outputs or the activation values of the neurons should have the correct output value, right. So, for example, one way of these neurons can have different kinds of functions that they can compute, of which one is where you compute the total input to the unit I as sigma wji, right, over all the inputs j, right, times the input that you receive from j. So, this was defined as the total input, right, and then we define the activation function as some g of this input, and that is the output that this neuron is going to have, right. And we saw that there can be different kinds of functions for g, of which the two most common ones are the sigmoid function, which looks like this, where the input changes gradually, or it could be a threshold function, which means that the moment you reach the threshold, it will simply switch on. So, it is off, when you reach the threshold it switches on, right. Yes, these ones, they are the input units, they are the inputs to your neuron, right. So, a neural network will have several layers of neurons like this, and will have one layer at the bottom of input units, right. In general, multi-layered, I am going to come to multi-layered networks. So, you will have an input layer, and then you can have many layers of neurons, right. So, this is a single layer, because just above the input layer you just have one layer of neurons. So, it is called a single layer neural network, and these single layer networks are also called, these neurons are called perceptrons, right. Okay. One, so this, the g function is going to determine that what is the output of the neuron, what is the activation value of the neuron A given the input that it is receiving, right, and input of the unit I is defined as follows, it is sigma over j wgi times ij, right. The first thing that we want to know is that how do we adjust these weights, so that given any function our neural network is going to adjust the weights in such a way that g of the input is going to have the same value as the output of the correct output of the network, right. So, we did a single step of error propagation. So, we said that okay, let us define the error. The error E is given as the square of the half of the square of the errors, right. So, this is the RMS error that we want to compute, root mean square error. So, this, and what is the error of the output? So, we are looking at, let me draw the neuron here as well. So, we are looking at the error that we are going to have in the output of this neuron, right. So, in general you can the total output is defined as the collective output of all these neurons taken together, right. So, it is a vector actually, right. So, when we talk about half of ERR square, it is that vector that we are talking about, and what is that error? That error is nothing but y minus okay, where what is y? Y is the true output, the correct output. Note that this is a vector, okay, this is a vector, this is a correct output vector, and its difference with HWX. And what is HWX? And what is X? X is the input, right, and HWX is the total input function that it receives, right. So, this is the total G of the total input function that it receives. So, we can write this as G over right, where again see we are dealing with vectors here. Okay. Now, let us look at how we compute the error in terms of the change in the weight values. So, what we actually need to see is how can we bring down the error by adjusting the weights, right. So, let us, how do we do that? So, if this is the error, then what we are actually interested in computing is the change in error with the change in Wj. And what is Wj? Wj is the weight that we are feeding into the neuron I, right. So, if we take a single neuron, then Wj means it is the weight of j to the output unit, right. So, let me recap what we are doing here. We have the neuron here, we want to compute that how do we adjust these weights, so that the error that we had on the output of this neuron is going to come down, right. So, if E is the error at the output of this neuron and W1, W2 through Wj etc. are the weights on these edges, then we are interested in finding out what is delta E by delta Wj, right, and that is going to give me the change in the error with the change in this weight, right. Likewise, we will do it for each of the weights, and that is going to give us the weight updating function. Right. So, if we use this formula, then let us see how we compute delta E by delta Wj. So, if we look at delta E by delta Wj, then this is ERR into, okay, let me first write down what was our E. So, it is delta by delta Wj of half of ERR square, right, where ERR was our y minus. So, our ERR was y minus g of sigma over j Wj, and xj is the input. Xj is the input here. It is the value of the input that is coming. Right. So, in Booleans it will be 0 or 1, but in general for a neural network it need not be 0 or 1. It can be anything. It can be any value. Right. So, this is Wj times xj or ij, whatever we might want to call it. Right. So, this is ERR. So, if we now apply this partial differential on this, so then we will, yes.
Xj itself is a vector for.
No, now when we are looking at a single weight updation, so xj is just a scalar which is the value of the input j. Xj is the scalar equal to the value.
For our neuron. This is the input for our neuron.
Yes, this is one of the inputs for the neuron. So, if you take a given neuron, if you take just one neuron, right, then these are the inputs that are feeding into that neuron. Xj is the value of the jth input. Wj is the weight of the link connecting the jth input to the output unit. Right. We will do the same for each of the neurons that we have in the upper layer. Right. So, we are doing it only for one of them, because you see when we are talking about the error, this error gets decomposed into the errors of the individual dimensions of the vector. Right. So, it is the error of this is one dimension, the error of the other neuron here will be another dimension. Right. So, now we are trying to see that how do we reduce the error in one dimension, okay, and we will do the same for all the dimensions. Right. So, this is going to be ERR times delta ERR by right. Now, we apply this, right. If we replace ERR by this term, then because y is a constant, what is y? It is a correct output. So, that is a constant, that is a value that is given to us. So, the differential will eliminate that, right, and we are going to have delta of this, right. So, we are going to have ERR, right, times minus of g of right. And now, when we use the differential on the g, so we are going to have this minus comes outside, we have ERR times g dash of in, right, times xj. Only xj is going to come out because the rest when we partially differentiate with respect to Wj, the rest will get eliminated, right. So, only so we will have only the Wj xj term will be significant, and when we differentiate Wj xj with respect to Wj, we get xj, right. So, this is the term that we have for the change in the error with respect to the change in the weight, okay. And that also gives us a way of learning in the neural network. So, what we are going to do is we are going to use gradient descent. So, we will just simply apply this rule to update our weights. So, for example, we will use Wj is can you see this color? So, Wj will be updated as Wj plus some alpha times ERR times G dash in times Xj. Right. So, this is the change in error with respect to this. So, if we add this term, then the error is going to decrease. If we add this term to Wj, then the error will decrease, because we had a negative here, right. And this alpha out here is called the learning rate. So, it is a fraction of the error that we adjust against the weights, right. See this term, the change in error with respect to the change in weight was negative, right. So, you will have to, if you subtract this from Wj, then your error will go down. So, if you subtract the negative term, it is equivalent to adding this thing, right. So, that is going to take, if you use this updation rule, then the delta E by the delta E by delta j is this. So, if you add this term, the error, the new error will be lesser. So, if you compute the total output with this Wj, it will come closer to the value y that we intended it to have, right. So, essentially what it means is that we just compute the error, right, and then use a fraction of that error to readjust the weights of the input to the unit, right. Now, okay. Now, how do we use this G dash in? So, for threshold functions, so G dash in is the differential of the input output function, right. So, it is the, so recall that we had different kinds of functions like the sigmoid, right, where this was in this direction we have the input, and in this direction we have the activation of the unit, right. So, this is our G function, this is our function G. So, if we compute the derivative of this, right, at any given input point, so it is a slope at that point, right. So, for the sigmoid function, I think it is just G times 1 minus G. Just let me check out. I think it is, yes, it is G times 1 minus G, right, of the input. And for the threshold function, recall that it is a step function. So, the derivative does not exist at this point. So, what was done was, in the initial algorithms for updation, this term was simply dropped. So, it means that you compute the error, right, times the input, and then take a fraction of that and adjust the weight accordingly, right. Now, is this part clear to you, this learning of single layer neural networks?
For some values of input,
yes,
the differentiation will be 0, then we just leave that.
Where can you have a 0 slope here, for example?
In that threshold.
In the threshold, see because this is not a continuous function, so the differential does not exist. So it was a design choice to simply drop this term, and it worked quite well actually, right. So then people started examining the performance of these single layer networks vis-a-vis other models of learning, like we had studied previously the learning of decision trees, right. And it was found that in some cases perceptrons would perform much better. For example, if you look at the majority function, what does the majority function give you? So if you have k inputs, right, if you have a unit and you have k input lines, right, and if a majority of them are 1, then this output will be 1, otherwise this output will be 0. That is the majority function. Now imagine trying to learn a majority function using a decision tree, right. So in a decision tree you will have these variables x1, x2 through some xk, right. Now if you just first examine the value of x1, suppose it is 1, can you decide which is the majority? You can't. Then you take x2, you find it 0, you still do not know what is the majority. So in a decision tree, if you just think that if in a decision tree you have to learn the majority function, then you may have in many cases to go right up to the maximum depth. In any case, without examining half of the variables you will never be able to decide, but even if you examine all the half of the variables and all of them are 1 or all of them are 0, only then you can reach a decision, right. So it is only in 2 cases that you will be able to reach a decision by examining half of the variables, right. But in order to reach a decision for all cases, you will definitely have to look at all the k variables, right. So if you try to learn the majority function using decision trees, it does not work too well, right. On the other hand, perceptrons can learn the majority function pretty well, because remember that they are good at learning a linearly separable function. Why linearly separable functions are better learned by perceptrons? Because we are individually trying to tailor each of the inputs independently, each of the outputs independently. So suppose we have 4 neurons and several input units, and obviously all of these are feeding into all of those, right. So what we were doing so far is trying to tailor these errors of these individuals so that the error is minimized, right. Now if it so happens that if you tailor this error, then for some other example the error is going to become larger, then we have a problem, right. But in case of linearly separable functions, where you have all the yes cases on one side of a hyperplane and all the no cases on the other side of a hyperplane, if you can separate out the yes cases and the no cases from this hyperplane, then individually if you move the dimensions towards this plane, then your error is going to progressively go down, gradient descent will succeed, and we will have learned that function, and the majority function is one of these cases, because if you look at the majority values, right. So they are all going to be on one side and the minorities are going to be on the other side. So you can always fit a hyperplane between the yes cases and the no cases, right. So that is why it was found that for such kinds of functions which are linearly separable, and for which decision trees are difficult to learn, perceptrons were very useful. But the moment when we came up with cases where the variable starts in the outputs are not independent in that sense and start influencing each other, then perceptrons will fare pretty badly. For example, if you look at that restaurant example that we had seen previously, for that what was found was that decision trees can learn that pretty easily and perceptrons fare really badly. So, people started arguing that what do we lack in the perceptrons. So, what we lack here is as follows, that if we look at a layer here, so if these outputs are not independent of each other, then there is no way of having a common variable shared between these two, which we could tune to bring the two into sync, right. So, what people thought of is, let us have a multi-layered network. So, we will have say something like this. So, we have some layers, an output layer, then we have some second layer, right, and finally, we have the input layer. So, this is a two layer network and we can generalize this to many layers. Between two layers we will have a complete bipartite connection. So, which means that this is going to be connected to all of these, likewise this is going to be connected to all of these, right, and similarly for this. And we will have a similar connection between this layer and these, right. So, each of these units connected to, right. Now, see, if you examine a weight here, suppose let us call this Wk, if you examine this weight, by tuning this weight I am able to change the activations of all of these output units, right, something which was not happening previously. See, we cannot tune the inputs, here it was only the inputs which was feeding into everything, but inputs are given, there is nothing to tune, and these weights are direct connections between inputs and the output layers, right. So, if we want to learn something which is in a sense a higher order kind of relationship, then we have here a mechanism of tuning these weights which is going to affect the activations of all of the output units. So, the question was that can we have a learning algorithm which will able not only to tune these weights, but also these weights, so that we are now able to learn functions which are not linearly separable. And then people say that okay, let us start from the top and try to see whether we can propagate the error backwards into these. See, what do we lack here? In order to update the weights that are feeding into this neuron, we need to know what is the error here, but error is given only at the output, because we know the correct output. We know the correct output and we can see what output we have got through our network, but we do not know what should be the correct output of this to get the correct output in the output layer, right. The training set that is given to us only gives us the final output, it does not tell us what should be the correct activation values of this hidden layer. So, this layer is called the hidden layer, we do not know what is the correct output of this. So, then the idea was that let us do the following thing, let us take the errors of these units and make a proportionate distribution of that error back into the hidden layer. So, that is why we have back propagation learning. We will compute the errors in the output layer and back propagate that error into the hidden layers, so that we have some heuristic for the errors that are there in the hidden layers. We do not know actual errors on the hidden layers, this is just we are guessing that if this fellow is feeding into all of those, then whatever errors that these fellows have, some of that blame goes to this one. So, we take a fraction of the errors from these propagated backwards into the hidden layer, right. And then once you have the errors or the guesses of the errors at these hidden layers, then you have the updation rules for these exactly as before, right. So, now let us go through this analysis quickly. So, at the output layer, okay, now this is just a 2 layer network that we have talked of. We can have a multiple layer network where we start at the output layer and then progressively start propagating the error backwards layer after layer until we reach the input layer, right. So, that is the multi-layer learning algorithm that we are going to formalize now. So, if we look at Wji, which is the weight from the, okay, let us follow this nomenclature, that this is the output I, output unit I, and this is, let us say, the hidden unit j, right, and this is some input k. So, Wji is this weight, right, and Wkj will be this weight, right. So, this is just this is one segment of this whole network that we have taken, one path, right, and obviously we will sum over the j's and sum over the k's when we do the analysis, right. So, Wji is simply given as Wji plus alpha, which is the learning rate, plus times Aj, where Aj is the activation of this unit, right. How do we compute the activation of this unit? By feed forward. When we present this network with a training sample, so we are feeding it with inputs x1 through xk, right. So, then we compute the activation of this as g of the total input that this jth unit receives, right. So, that is the activation Aj, right. Similarly, when we have the activations of all of these, then we can compute the activation of Ai as g of ini, where ini is sigma over Wji A of j and summation over j, right. So, that is how we compute the activations of all of these given one training sample. After doing that, we will back propagate the errors, because the training sample will also have the correct output values, which we will compare with the Ai, then back propagate the errors, adjust the weights, and then again present it with the second training sample, and continue doing this until we have run all the training samples several number of times, and we hope that the neural network has learned the function. At that point of time, we seal the weights and thereafter evaluate the performance of the network on the training samples and on new samples of the data, right. That is what the whole learning is going to do. So, the updation rule for these weights between the output layer and the hidden layer is Wgi is Wgi plus alpha times Aj times delta I, where delta I is that function that we had seen, it is basically ERRI times G dash ini. Now, recall that the overall this thing was the learning rule between the from the output layer was this, which we had already derived. So, this term is the delta, right. We are just using this term for the delta. So, it is just a short form. So, this is that ERI times G dash in I. So, this is the rule that we will use for updating this one. This part is very simple, it is exactly as before, right. Now, comes the question of how do we compute the errors in these units. So, that is where back propagation will come in. So, we will define delta j as G dash in j times sigma over I W j I delta I. Now, I have not yet derived this, I am just stating this, we will derive this later, but intuitively let us see that what is this error term for delta j that we are having here, right. This is G dash of in j, just like we have G dash of in I, and then instead of ERR I, this is the error that we are approportioning back into the hidden layer. And what is this term? This is sigma over all I Wji times delta I. What is sigma over this? So, it means that this j unit is feeding into other neurons as well in the output layer, right. You take the errors of all of those, right, take proportionate with the weights of the links connecting to those. So, it is sigma over I, mind you. So, it is the sigma over all the output layer units, right, and that fraction is what we are going to approportion back as the error of this. So, that is going to be, this term is going to be our ERRJ term that we obtained by back propagation learning, right. Now, this term, how we arrive at exactly this term I will formally derive later, but as of now you can appreciate that this is something which is the errors of the all the output layer units biased by the weights of the connections from this hidden layer unit to those. So, it is fair enough that it is proportionate to this is what the error coming back should be, and we are the proportionality function is this G dash in j. Okay. We will derive this later, but now if we have this as the error here, then the remaining part of the updation rule, which means how do we update Wkj, sorry, k comma j, this is going to be exactly as before. So, we are going to have Wkj plus that alpha into Ak into delta j, where Ak is the input. If you have multi-layer networks, then it is the Ak is the activation of the next layer of units. Otherwise, in case of this, Ak is the same as Xk, it is the input to this, right. So, see, as you can see that these two are absolutely similar. So, the whole trick is in computing this one, in apportioning the error at the output by back propagating it backwards into the hidden layers, right. So, we will now derive the formal basis for this. The other part of the updation is as before, and it has the same derivation as for just a pair of layers. Is that clear? Now, let us get into the derivation of this one, right. So, let us see what we want to actually derive. We want to actually derive the change in error with the change in Wkj, right. So, what we are interested in is how does changing this weight affect the change in the error at the output layer. So, delta E is the error in the output, change in error in the output layer, and we are interested in finding out how does these links, weights of these links affect those, right. Now, in case of just 2 layers, this error would get split up into the individual outputs, because the link is only connecting one input with one output, but in this case this link is actually affecting the weights of all of these links in an indirect way. So, each of these links are dependent on this. So, we cannot separate out the i's as we were doing in the case of 2 layers. So, that means this is going to look like minus of sigma. Okay, what is our error? Let me bring back our error term, just a minute. Yeah, this was our error, right. It was the let me rewrite, it is half of y minus ai square, because this hwx is actually the ai in our case. Now, this is activation of the output layer unit, right. Now, if we differentiate this with respect to wkj, if we differentiate this term with respect to wkj, this one, then we get minus over sigma over I yi minus ai, because see this is for just one unit. If you take it over all yi's, which means all the output layer units, then you get yi minus ai times delta of ai by delta of wkj, right. So, it is simply differentiating that error term with respect to wkj, but because wkj affects all the activations of the output layers, so we cannot eliminate any of these. So, they are all there with the sigma, right. So, then I can simplify this as sigma of over this thing yi minus ai delta over g, this ai is g over in I, g of in I times delta wkj. Now, what do we have here? If we this will become g dash of in I, this one, right, and delta over in I now. What is in I? In I, what is I first of all? I is the out, is this one, the output layer unit. So, in I is sigma over wji, sigma over j wji times aj, right, that is the total input. So, we get, okay, we write this as minus over sigma over I, okay. This term is our delta I, because this is our ERRI times g dash in I, and remember that we had defined delta I as ERR times g dash of in, right. So, this is delta I, and then when we differentiate this, we will have wait, we will have, okay, let me not jump steps. this is going to be sigma over j wji aj, right, aj. This is clear. This is just rewriting in I as w sigma over this and then taking this term and calling it delta I, that is all. Now, when we propagate this in, what are we going to have? We will simply have the wji term coming out, right, because we are differentiating with respect to wkj, right. We are it is still there, I am not yet done. So, it is wji times delta over aj by delta over wkj. No, wji is there because you have wji times aj, wji is a constant. Wji is a constant because you are differentiating with respect to wkj. So, if you differentiate wji with respect to wkj, you will just have wji because that is a constant. See, this is this times this. So, it is the coefficient. The ones which do not have j will their sum over this, right. So, those terms will get they are just individual constant terms. So, they will get eliminated by the differential, right. Only those terms which has aj involved will remain and the coefficients of those will come out here. So, the only term which has aj here is wgi aj, right. So, wmi, suppose if you look at a term in this summation, if you have a term wmi am, see this is totally constant with respect to wkj. So, this whole thing is going to get eliminated because of the differential, whereas when you have this one, well, aj is not independent of wkj. So, therefore, this coefficient will come out and you will have the differential propagating into aj, right. This is clear.
So, we need in I as w in the previous paper.
Yes.
We have in I has been as the sigma summation over wgi.
Wgi aj. This is the whole in I.
So, we have how come j comes in this term?
In which term?
Independent of j. In I.
Okay. If just do not treat this j as the j here. Okay. It is my mistake. Just instead of this j, call it something else. Call it j dash. Right. Now, this j that we are talking about here, that is also there in this among this set, right. That is the fellow which is coming out. Clear? I use the same variable here, so that is probably confused. Now, is it clear? So, this we have derived. Then, so let me have it here. I have this. Then this is equal to sigma over I delta I wji g dash in j times delta in j by delta of wkj. How do we get this? Because aj, our aj is nothing but sigma, sorry, it is just g of in j. right. So, A j is g of in j. So, if we apply the differential on that, we will have g dash in j coming out, and we will have delta of in j by delta. Then again expand out this term. What is this in j? Okay, let me write it down. Sigma over I delta I w j I g dash in j delta over delta by delta w k j of sigma over, okay, this time let me write k dash, right, w k dash j a k dash, right. Again by the same this thing, out of these only the terms which have k in it, they are going to come out. So, we will have this as minus, what did I do with the minus? There was a minus here, I forgot, right. So, we will have minus over sigma over I delta I w j I g dash in j times a k, right. That is the only term which is going to come out, because w k j a k will be there in this set, and because we are differentiating with respect to w k j, we will just have a k, right. And this is what we are referring to as a k times delta j, right. Now, is this what we had hoped to get? So, this is exactly what we are doing here. See, we are adjusting w k j as w k j plus alpha times a k times delta j, right. So, this explains the updation rule for the other layers, except the updation rule for the weights feeding into the output layer, right. So, quickly to conclude, what is the algorithm then? The algorithm is, we start with the neural network, say single layer, multi-layer, whatever. We start by presenting with it with a training sample. We present the training sample, compute the updation, the activation values of all the units until we compute the activation values of the output layer units. Then compare the outputs that we have received with the training sample outputs to compute the error. Having computed the error, our objective is to readjust the weights so that the error decreases, so that with the changed weights, the new activation values will be closer to the real values, to the correct values, right. Having adjusted the weights for one training sample, we will again resume with another training sample and again readjust the weights. Every time we use a proportionality factor called alpha, which is the learning rate, to decide on how much we are going to adjust, right. So, you can learn fast, you can learn slow. Slow learning is better learning in general, because you are doing gradient descent, so you are more likely to come down into the global minimum, and then you continue with this learning for this different training samples until ideally you reach a state where the weights are not changing too much. So, if the weights are not changing too much, which means that you have converged on the correct set of weights, right, and then you freeze the weights and you say that I have learned the function, right. And in order to do this error computation, we have studied the backpropagation learning, which computes the error at the output layers and then apportions that error back into the hidden layers, and then once we have the errors for the hidden layers, we use the 2-layer learning algorithm to readjust the weights, as we have seen by the weight adjustment formula, right. It has been found that more than multi-layer neural networks perform better for cases where perceptrons were not working well. For example, with a 2-layer network, the restaurant example that we saw was learned to a much better extent. The decision tree was still better, but only marginally, right. It is still very not well intuitively understood that what happens if you have more than 2 layers. I mean, the claim is that you will learn better and better functions, but there is no formal way to establish that as of now. But still we are looking at different kinds of architectures for neural network and see how you can learn them. So, in the best interest of time, we will close this chapter here, but there are actually lots of published papers on learning different kinds of functions using neural networks and other kinds of models, right. So, if you are interested, you can look into different kinds of things, and there is a specialized course on machine learning also offered by our department. Thank you.
Indeed, in this golden jubilee year, as the celebration continues, Pandit Nehru would surely have been a proud man today. For him, IIT Kharagpur was always more than just an institute of technology. In his own immortal words, it is indeed